Oh, yeah.
In amateur radio, the term mode of operation, often shortened to just mode, refers to how the radio signal is transmitted, received, and interpreted. Essentially, mode is the method or format of communication being used between amateur radio operators. A mode of operation describes the technical method of modulation and signal processing a radio operator uses to send and receive information. It determines what the transmitted signal looks like and how the receiver must decode it. In order to put this in perspective, I need to go over some important concepts: band, frequency, and mode. A band is a segment of frequencies grouped together because they behave similarly in terms of signal propagation and are designated for particular uses. A band in amateur radio is simply a defined slice of the radio spectrum reserved for amateur radio use. Each amateur radio band is identified by its approximate wavelength in meters or frequency range in megahertz. Each band has unique properties that determine how far signals travel by ground wave, sky wave, or line of sight. It also determines when frequencies work best. This also impacts the type of antennas used and how they perform. In simple terms, frequency is the number of times something repeats in a given period of time. In radio and electronics, frequency means how many cycles of an electromagnetic wave occur every second. Higher frequencies like VHF, UHF travel mostly line of sight, good for local or satellite communication. Lower frequencies like HF can reflect off the ionosphere, allowing long-distance communication around the world. Frequency is a number that designates where you are on the radio wave spectrum. For example, if I have my radio set at 14.215 MHz, I am in the 20-meter frequency band. Mode is the form of communication, or more clearly, a modulation technique used on a given frequency band. It determines the shape, bandwidth, and characteristics of the transmitted signal. In radio communications, modulation is the process of imposing information, such as voice, Morse code, or data, onto a radio frequency, RF, carrier wave so it can be transmitted through the air and later decoded by a receiver. The mode used determines clarity and reliability of communication given the current propagation conditions. The mode used impacts power usage, antenna requirements, and signal range. Understanding the benefits and liabilities of each mode helps operators choose the best mode for propagation conditions. When making comparisons between different modes of operation, the noise floor is an important part of the discussion. The noise floor is the level of background radio noise present in a receiver or in particular radio environment. The noise floor is made up of natural and man-made noise sources. It is the baseline signal level, below which incoming signals cannot be distinguished. In other words, any signal weaker than the noise floor will be lost or become unreadable. In this video, I will contrast the three modes of communication used by amateur radio operators. These modes are CW or Morse code, analog radio, and digital radio. Let's get started. In amateur radio, bandwidth refers to the range of frequencies that a signal occupies on the radio spectrum. It's measured in hertz, but typically measured in kilohertz or megahertz, and represents how wide a transmitted signal is. Using wider bandwidth allows the signal to carry more information, for example, voice signals or fast digital data. Narrower bandwidth signals take up less space on the band, allowing more operators to use nearby frequencies without interference. CW has the narrowest bandwidth, which means when using CW, the receiver is only listening to a tiny slice of the spectrum. That slice includes the desired signal, your CW tone, and very little surrounding noise. Digital mode has the next smallest bandwidth, with analog coming in last, having the largest bandwidth. Power management is the practice of using only the amount of transmitter power needed to make reliable contacts, no more, no less. This is especially important when working in the field using battery power. The power of a transmitted signal is spread across its bandwidth. If two signals have the same total power but different bandwidths, the narrower bandwidth signal has more concentrated power per hertz and a higher power density, making it easier to detect weak signal conditions. The wider bandwidth signal spreads the same power over more frequencies and has a lower power density, making it harder to detect weak signal conditions. Poor propagation refers to unfavorable conditions for radio signal travel through the Earth's atmosphere or ionosphere. Under poor propagation, radio signals weaken, fade, or fail to reach distant stations. The ionosphere may not reflect signals efficiently. Noise absorption or distortion increases. Reliable long-distance (DX) communication becomes difficult. Simply put, poor propagation is when atmospheric or space conditions reduce a radio signal's ability to travel long distances or maintain strength and clarity. This is where CW and digital radio shine. Human decoding is the art and science of using your brain to interpret weak, noisy, or incomplete radio signals. Human decoding refers to the ability of a radio operator to interpret and understand information directly by ear, without relying on a computer or electronic decoder. It's when your brain becomes part of the communication system, detecting, filtering, and interpreting radio signals through listening and practice. Human decoding is the operator's mental processing of imperfect radio information to recover meaning. This is important because it extends communication when machines fail. It keeps amateur radio human-centered and skill-based. It provides independence from technology in emergencies. It preserves the tradition and craftsmanship of radio operation. When talking about equipment complexity, the discussion involves issues like what type of mode will be used based on the current propagation conditions, along with equipment compatibility, portability, and ease of equipment installation. Using simple equipment makes installation easier, operation smoother, and maintenance simpler. Equipment complexity directly influences decisions about the size, weight, and layout of your station, along with the cooling and power system you need. The concept here is to use as little equipment as possible to ensure the ease and reliability of every contact you make. Efficient radio systems don't just save energy, they save time, space, and frustration. When a disaster strikes like hurricanes, earthquakes, power grid failures, or internet outages, normal communication networks can collapse. Amateur radio remains effective because it operates independently of infrastructure, uses battery, solar, or generator power, communicates directly from station to station, and uses simple, reliable modes that adapt to poor conditions. Seasoned operators understand that different modes have different strengths in emergency scenarios. CW is the best all-around weak signal performer, simple, works with very low power, and doesn't require a computer. Single sideband or analog radio is best for natural communication, but suffers badly in weak propagation. Digital radio is extremely efficient, sometimes better than CW, but relies on computers, limiting back to basics, emergency use. Each mode in amateur radio has its own role to play, from the simplicity of Morse code to the clarity of analog voice and the precision of digital signals. Together, they form the foundation of communication, reliable, adaptable, and always ready when other systems fail. Amateur radio is more than a hobby. It's a living science that connects people, ideas, and the world through the airwaves.